Hi, I'm Nick Rabinowitz. I'm a senior staff engineer at Foursquare, and I'm here to talk about the power of hexagons, how H3 and Foursquare are transforming spatial analytics. So, quick overview of what we'll be covering in the talk today. I'll give a brief intro of myself and of Foursquare. We're going to talk about grid systems, geographical grid systems, and how they can be used in spatial analysis. We'll talk specifically about the H3 library, which is a hexagon-based grid system. And I'll go through a fairly in-depth walkthrough of how you might use H3 in practice, and then we'll have some Q&A at the end. So, hi, I'm Nick. As I said, I'm a senior staff engineer at Foursquare. I have been working for the last year and a half or so at Unfolded, which became part of Foursquare about 9 months ago. Unfolded is a spatial analytics company with a UI-based spatial analysis application that allows everyone to use and create beautiful data-rich maps. I've been a software engineer for many years, and for the last 10 plus years, I've been focused on mapping and data visualization. And for the last 5 or 6 years, I've been working on H3, and I'm the core maintainer of H3.js. And I like to say I'm secretly an English major, though that gets less secret every time I say it. As I noted, I started working at Unfolded as a startup about a year and a half ago. 9 months ago, Unfolded became part of Foursquare. I like to think of this as saying that we were a data analytics company with no data. Foursquare was a data company with no analytics. Put us together and we can do some amazing things. And I'm here to talk about geographic grid systems. So what is a geographic grid system? The fundamental fact is that the real world, real geography is really messy. It's filled with things. And those things are really difficult to model in a meaningful way without knowing very specific use cases. We don't have, geometry in the real world. We don't have points or polygons. We have real things. And it's very difficult to deal with those from a data perspective. This is why Marc Monnier says it's not only easy to lie with maps, it's essential. And what he means by lying with maps is choosing what to represent and how to represent it in a geographic context. Every map makes a bunch of choices and you could say lies about other things that it leaves off. So maps are a way of taking all this messy real world data and abstracting it into simple forms that we can work with and easily represent. The most common ones are points, lines, polygons, this kind of geometry that we use to represent real world objects and phenomena. Geographic grid systems are one step further. They're also known as discrete global grids, and they take another kind of abstraction where they break the world up into sets of uniform cells. And it takes the entire geographic space and turns it into this really clean mathematical space that you can work with as an analyst. So these cells provide a common unit of analysis that isn't biased by the kinds of things that bias our other maps and supports a variety of algorithms that are hard to do with traditional geometry or traditional map modeling. Just as a quick comparison, other ways that people represent particularly area data tend to be via administrative boundaries. So those are, state or county lines or provinces or zip code tabulation areas or things like that. And what I like to say about administrative boundaries is that every administrative boundary was made for somebody else's use case. They were all made due to a variety of historical, legislative, geographic reasons that are probably not your reasons. Zip code areas are meant to facilitate postal delivery, and unless your analysis is really tuned in to postal delivery, that's not going to be a great area for you. It's not going to be a great way of dividing up the world. You can also divide up the world into other kinds of grids or bins. You can divide any map you can divide up into a bunch of squares or a bunch of polygons. But a geographic grid system gives you a stable grid that never changes, that can be shared across systems, shared across analyses, And it has unique identifiers for every grid cell that can be shared across systems. And that makes it really easy to join different data sets and bring together different things for analysis. I'm talking about grid systems rather than just grids, because most grid systems are made up, in fact, of multiple grids. So usually these are related. And in the case of H3 and many other examples, they have a hierarchical relationship between the grid cells. So you can see you've got large hexagons containing smaller hexagons, containing smaller hexagons. So you have these parent-child relationships between layers that allow you to easily move between different coarseness and fineness of resolution. You can choose the granularity of your data analysis by choosing the grid you work with. So there are other grid systems. Probably the simplest and most commonly used is just the graticules. So the lines of latitude and longitude can be used to split up the entire world into a grid system. And you can also use similar divisions for things like web Mercator tiles, which are a very common tool used in web mapping systems. These have a lot of issues. The main issues that the graticule and the web Mercator tiles have is that because they're both based on Mercator projection, you end up with huge distortions as you get closer to the poles. More advanced grid systems like S2 or H3 aim for equal area cells that are comparable across the entire world, no matter where they are, even close to the poles. So the H3 system has chosen to use hexagons for its grid. And you may ask, why hexagons? Why not, well, squares would be probably the most obvious choice. But you could also go for, ducks and fish if you really want. There are lots of shapes that can tile the plane. Why would you choose one shape over another? What's the analytical reason you might choose it? So what makes a good grid cell? There are a lot of characteristics that make a good grid cell. And by a good grid cell here, what I really mean is a cell that suits many purposes for different kinds of analysis, a good general purpose grid. The first thing we want is generally uniform shape, uniform edge length, and uniform angles. The reason we want these things to be uniform is because every time you have things that are, one way in one part of the cell and another way in another part of the cell, you often have to correct for that in different kinds of analysis. So we're trying to keep things as uniform as possible. And that already just brings us down to regular polygons. And then in fact, only to 3 regular polygons, because there are only 3 polygons that can tile the plane: the triangle, the square, and the hexagon. You also want these cells to be optimally compact. So one way to think about this is you want to minimize the standard deviation of distance from the center of the cell. And you can see that with a triangle, you've got some points within the cell that are right at the edge, but are actually fairly close to the center. You'll have some points within the cell that are right in the corners and are fairly distant from the center. This is a little bit better in a square, and it's even better in a hexagon. Hexagons are the most compact in this terminology of the regular polygons. You also want the cells to be optimally space filling. So one way to think about this is if you take an arbitrary polygon, let's say a building footprint or a state boundary or something like that, which set of cells is going to be best at representing that shape with the smallest margin of error? So I don't have a mathematical proof here, but I believe it to be true that hexagons are of equal area. Equal area hexagon is going to be better than an equal area square or an equal area triangle representing an arbitrary shape. You get smaller margin of error around the boundaries. Another thing that's really important to some kinds of analyses, and this is one of the biggest reasons we chose hexagons, is uniform adjacency. You can think of this as, do I have one class of neighbor or do I have multiple classes of neighbor? With triangles, you have many classes of neighbor that meet at the corners, as well as one class of neighbor that meets at the edges. With a square, you have 2 classes of neighbors. You have corner neighbors and you have edge neighbors. With a hexagon, all of the neighbors are equal. And the transition from one neighbor to the next is uniform across the entire grid. And this is really helpful for the kinds of analyses where you're trying to, for example, traverse the grid in one way or another, or spread out your data. Let's say you're doing a smoothing operation. Having uniform adjacency is really powerful, and makes a lot of choices much easier because you don't always have to choose between class A and class B neighbors. Another really important characteristic is hierarchical relationships. Ideally, hierarchical relationships in which the parent perfectly contains the child. This is the one place where I think hexagons lose out. They can have hierarchical relationships. There are several ways to do this. The way we do it in H3, you can see on the right here. But they don't perfectly contain their children. You can see that a triangle can perfectly contain its children, a square can perfectly contain its children, a hexagon can almost contain its children. The good thing about this is that even though that is imperfect, it has a fixed margin of error, and that margin of error is stable as you go down. So it's the same margin of error between an ancestor and its grandchildren as it is between an ancestor and its children. Finally, a really important characteristic of a discrete global grid is to have low shape distortion and low area distortion. These are characteristics in general of map projections. And the way that you construct most global grids is by picking some sort of map projection and picking some sort of projection surface. Now, many map projections that you might be familiar with, like Mercator, use the cylindrical projection surface. But this has a lot of downsides and singularities, particularly around the poles. So most global grids are built on polyhedra that allow you to have multiple projection surfaces, minimize the distortion, because the more projection surfaces you have, the less distorted each surface will be. And that allows you to have these global grids with relatively low shape distortion, relatively low area distortion. Now, the more projection surfaces you get, the better. And so the icosahedron, the 20-sided regular polyhedra, this is the most faces you can get in a regular polyhedron. The icosahedron is going to be the best option here, but you can't tile an icosahedron with squares. You can only tile it with triangles, or as it turns out, with hexagons. And so by choosing a cell shape that can tile the polyhedra that we want, we can minimize our shape and area distortion. If you compare us, for example, to S2, we have a much less distortion across the globe than some of the S2 cells, which are square but turn into real diamonds toward the edges of that cube. So these are the many reasons why we think that hexagons win out and why we chose hexagons when we were constructing the H3 grid. We give up a little bit. So we give up a perfect child containment, and as I'll talk about in a little bit, we also give up a perfect uniform shape. But we don't make huge compromises in those areas, and I think that overall, the hexagon lends itself really well to a general purpose grid. It's also been noted, and I hear this argument a lot, that hexagons just look cool, and that's the reason why you might have a hexagon-based grid. I would make the argument that hexagons look cool because they are cool. In fact, looking cool is a representation of how good they are at representing data, because our brains are amazing visual processors, and we can understand at a relatively low precognitive level that a hexagon is going to represent the data better than a square. And that's part of the reason why a large hexagon-based data set might look a little bit better than a large square-based data set, because it actually represents your data better on a map. So that brings us to the actual H3 library, which I helped to build with my colleagues originally at Uber, and now I am continuing to work with colleagues on it at Foursquare. So the H3 grid is built on the icosahedron, and you can see we've basically taken an icosahedron, we projected it onto the surface of the Earth. We take each triangular, or now spherical triangular face of that icosahedron, and we cover it with hexagons. And then we subdivide and subdivide and subdivide. And we go down from the top level that you can see here in the top right. This is called Res 0, and these are roughly continent-sized almost cells, down to resolution 15, which is about under a square meter. So you can index any place on Earth with a fair amount of precision using these H3 cells. And every one of these cells has a unique identifier. I mentioned before that we're not exactly uniform in shape, and that's because it's not actually possible to tile a sphere with hexagons. You have to have some pentagons in the mix. And you can see why. If you're tiling this on top of an icosahedron, every time you get a vertex, you've got 5 faces coming together. that's just not going to be able to be split up into a hexagon. So we end up with these pentagon cells. The good news is there are only 12 at every resolution, and as you get finer and finer, those 12 get smaller and smaller until you can generally ignore them. You can particularly ignore them because we have chosen an orientation of the icosahedron on the Earth where all of the vertices fall in water. This is called the Dymaxion orientation, something we borrowed from Buckminster Fuller, who was a well-known physicist and polymath in the early 20th century, who came up with this orientation of the icosahedron so that we could maximize unbroken land. So that brings us to the H3 grid, which can cover the Earth and can index it at any point. The H3 library, which we built to represent the grid and to work with the grid, is an open source project. You can read more about it at h3geo.org. It's built in C. We chose C because it's extremely fast and extremely portable and easy to create bindings for other languages. So we have all these other languages, Python, Java, JavaScript. You can easily work with the H3 library in those languages and work with the tools of your choice. We also have extensions for database systems like PostgreSQL and BigQuery. I won't go in depth into the functions of the library, but just to give you a general idea, we have indexing functions that are going to allow you to take any point and find the cell that it belongs to, or find a cell and give you the point for the center or the polygon for the boundary. We have hierarchical functions that allow you to go between cells and their parents or their children. We have traversal functions that allow you to find the neighbors of a cell for any given distance or to find the path between any two cells. We have functions for dealing with regions. So we have the ability to take a polygon, give you the cells that come within it, or to take a bunch of cells and give you the polygon for the outline of those cells. And there's a bunch of other utilities and other things that you need when you're working with these cell models. So I wanted to give you a quick run through, and it's going to have to be pretty quick, but I'll try to get as in-depth as I can in the time we have, about how to use H3 in practice. And I'll do this visually because I think it's the easiest way to understand what's going on in an H3 analysis. So in this particular case, I'm starting off with a whole bunch of points. Frequently, we have point data sets that might represent physical objects, that might represent events. In this case, they're representing crime events within the city of Oakland. And we might have a bunch of questions we want to ask about these crime events. How does crime vary across the city? What patterns can we see? Maybe we have a particular use case, like we want to perform site selection. So we might want to find the right place for a business, for an intervention, for our house, and we want to consider the impact of crime on those decisions. So as you can see, a point data set, it can be interesting. You can get some sense of things like density, but it can frequently be difficult to work with, particularly if those points are frequently overlapping, which they probably are in Oakland. You can see these things are probably happening on city streets. And so you might have lots of things on city streets that overlap and are hard to distinguish visually. So the first thing that we generally do when working with H3 is to take whatever data set we're working with, be it points or polygons or something else, and to index it into H3 bins. You could say we're binning it into H3 cells. And here we're doing probably the most common H3 operation, which is simply we're grouping things by H3 index and we're aggregating by count. So this is a view of those crime statistics, but with counts by cell. And as you start to do an H3 analysis, you're going to choose, is this too coarse or too fine? What's the right granularity for my analysis? So in this case, we might decide that resolution 9, which we had here, is too coarse, and we really want something a little finer grained. Here we have resolution 10, and it gives you a slightly better picture of the distribution of crime within the city. You start to distinguish things like roads and freeways. You don't have to aggregate by count, of course. There are lots of other things you can do. Here I'm aggregating by mode. This is the mode of the type of crime. And you start to see other kinds of patterns. So you can see that there's more of this sort of brown image toward the downtown of Oakland. This is things like muggings and robberies. Whereas violent crime, homicide, etc., is orange, and you can see that there's a greater distribution of that as we move south. As we move north, it's more about home and car burglary. So when you aggregate a data set by counts, and when you see a density map of any kind over a city or over the United States, probably the first thing you're thinking of is this just a population map? Are we just seeing crime as a representation of population density? And that's certainly possible. So one of the common ways you might address that is to try to normalize by population. So one of the great things about H3, one of the most powerful things that it offers as an analytical tool is the ability to bring lots of things into a common unit of analysis. So here we are taking census block groups, and we have disaggregated those block groups into H3 cells, weighting in general by the amount of a block group that fits within a cell. And now we have census data that's at the same unit of analysis as our crime data. We can stick these things together and we can do cell arithmetic, where you basically, within each cell, you perform some calculation. And now you can normalize by population simply by dividing the crime numbers by the population. Now, there may be other things you have to consider there. For example, places with 0 population are going to get blown out. But roughly speaking, this is how you might consider a population normalization function. And you can see as we do it, that you get a slightly different view of the distribution. You can see that there's a lot of crime sort of in the middle of the city that starts to look much more like just population when you normalize. And you can see that there are other kinds of hotspots, particularly around freeways and downtown, that start to look like they're more interesting because they represent high crime, even after you've normalized by population. This gives you a quick view of what it's like to take many data sets and stick them together when they have a common unit of analysis. One of my favorite examples for using this technique is suitability analysis. Suitability analysis is a GIS technique that I like because I'm not a data scientist and I find it really simple. And I appreciate the simplicity of this analysis. You basically take a whole bunch of metrics that you care about, you convert them to a common spatial unit. In this case, the common spatial unit is the easiest part. We're going to convert them all to H3 cells. You normalize them all, usually between 0 and 1. You join them all together, so you have one, gigantic data set with many columns. You assign usually subjective weights to each of those columns. So if I'm taking these different data points and I'm bringing them together, mean income, proximity to transit, urban development, I'm going to say which ones matter more to my particular use case and assign some weight to them. And I'm just going to add them all together, and that gives me some kind of suitability score that represents some overall picture of my my suitability. So suitability here is really talking about, I'm looking for the best location for a particular thing, be it a building or an intervention or what have you. You can think of this as sort of taking all these layers of data and mashing them together into a data sandwich. This is very hard if your data is in a variety of formats, and becomes relatively straightforward when your data is all in a common unit of analysis. And that's what H3 really offers in many cases. So quick example of using this in practice. We have a proportion of high income households. I'm imagining a use case here. My imagined use case, and I should have come up with a nice image for this, but my imagined use case is I'm trying to find a spot for a new restaurant. And my new restaurant, I'm going to call it the Oxford Don. It's going to cater to wealthy professors. And so I'm looking for places with high income households. I'm looking for PhDs because they're going to be really good customers for my new restaurant. I might want to be near other restaurants. So I might want to be in a restaurant-rich area so that people will already be coming there for dining. Whether or not being near competitors is a good thing or a bad thing for suitability analysis, we'll take this off the table for now, but we'll assume for the purpose of this example that this is a good thing. And I also want proximity to hotels because, as we all know, rich professors are constantly flying into town for conferences. And so for this example, these are the things I care about. I'm going to assign weights to all of them. I'm going to add them all together, and I get this overall suitability score. And what this is essentially, I think of it as a surface. So a surface, when I talk about a surface with H3, I'm talking about a fairly contiguous area of cells with some continuous variable that changes over that area. So you can think of a surface as literally being a surface, you can use elevation as an almost literal surface and represent that as H3, or you could use any continuous variable that you want to investigate and use that as a surface that you're going to look at over a geographic area. In this case, you get some hot spots, you get some cold spots. I might be most interested in the very highest areas, and so then I'm going to start filtering down. And when I filter down, I start to get some really interesting areas, the places where my scores are really highest. And you can see they're probably not too surprising. If you're familiar with the Bay Area, you've got hot spots around UC Berkeley and Stanford. You've got hot spots in San Francisco. These are places where my high-end, high-education restaurant is going to be a perfect option. And when we, investigate, we look and zoom into one of these areas, for example, in Palo Alto, you can see the breakdown. We've got these different, weighted variables that we have chosen here about top earners and top PhDs and how close you are to hotels and restaurants. And we've been able to calculate this suitability score, which you see at the bottom here, which is an overall picture of how suited this particular area might be to my use case. This is a really good technique for a lot of different things. I would say, generally speaking, it's, the most obvious use cases are things like retail or placing, new restaurants or new locations for a business. But you might have lots of other cases where this would work out as well. You can think of applications for this kind of analysis in logistics, or even, as I said before, if you are, looking for places to do different kinds of interventions or different kinds of city planning, initiatives to change things about your city, this might be a way to address it. There's a lot more you can do with H3. This sort of scratches the surface of the kinds of things that H3 is really good for. Spatial indexing is probably the most obvious, but you can also do things like radius search. It makes for a very fast radius search within a database. You can convert raster data very easily to H3, probably much more easily to H3 than to many other geographic forms, and work with it and easily join it with your other data sets. You can do clustering and find areas of interest within your city that meet some particular criteria. You can interpolate surfaces or smooth over surfaces so that you can create a broad surface and have data where you didn't actually have point data in your original data set. You can do things like similarity analysis and anomaly detection. You can imagine that because we're dealing with these uniform cells, they're a lot like pixels, and they actually work very well in pixel-based machine learning contexts. So you can apply tensors to them. You can spit them out and come out with a new surface of pixels that represents, for example, a forecast or a prediction about what you're going to find based on the data that you input to your model. You can do things like flow analysis, or, as I said, suitability analysis, and there are many more. It's a very versatile tool for working with geographic data, particularly if you don't have the heavy GIS background and tools that are usually required to deal with more complicated types of geographic models like polygons or raster data. Before we break, I wanted to give a quick shout out here to a project that I've been working on at Foursquare, which leverages H3, called Hex Tiles. So Hex Tiles are a new tiling system based on H3. As we went over in this suitability analysis example, it's really great to be able to bring in many different data sets in your area of interest. And as we all know, prepping those data sets can take a bunch of time. It can be a really difficult and time-consuming process for the end user. The benefit of Hex Tiles is that it allows Foursquare, which is fundamentally one of the things that we're best at, is providing really interesting data sets about places and about foot traffic and visits. We can put these data sets together into these tiled data sets, which allows us to partition massive global data sets into relatively small, manageable chunks that we can either bring into a browser or into a notebook for analysis, one at a time, just the parts of the data that you need, and easily join with each other so that you can perform analysis across many different data sets. And this allows you both to work with this at a data level within a notebook to come up with some overall answer, and to visualize and explore data within our browser-based application. Fundamentally, and I've seen this in several different organizations now, one of the great things that H3 provides is this ability to build a whole ecosystem. Frequently, geographic data tends to be in little silos in different parts of your organization. H3 gives you this common key across those silos that you can easily use to join data from different parts of your company, bring it together, and create something great. Thank you. I hope you enjoyed this talk, and I hope you learned more about us. You can see our contact information here. You can follow me on various platforms, including Twitter, LinkedIn. I'm at nrabinowitz on most social media platforms. You can learn more about H3 at h3geo.org, or you could go to studio.unfolded.ai to try out our studio application and work with H3 data and Hex Tiles yourself. Thank you. I'm going to go over to the chat room. There's a chat room for Q&A here. If I don't see any questions pop up there shortly, I will ditch the live Q&A part of this and move to an offline Q&A. But I appreciate your time, and please ask if you have any questions. You can either ask in the Q&A channel, or I assume you could probably also ask in the GoToWebinar channel. There's a link in the chat channel, by the way, to the Q&A channel that we're going to use for this session. I don't know if anyone has questions. If you have questions that you don't want to bring up in a public Q&A, or if you'd just like to get in touch, I would encourage you to join the Slack channel that's on this slide, and we'd be happy to talk to you more about H3 or about the Unfolded platform and how it might work for you. All right, I don't see any questions come up, so I'll assume that all questions will come in offline. I hope you enjoyed the talk. Thanks so much for taking the time with us.
Thank Thank you for speaking, Nick. We are very grateful to those who have attended this session, and we will now start our short survey. The survey helps us shape the future conferences. Thank you.